Hi, let's meet the wonderful members of Hisham's family. First, we have Noor Insyirah, binti Ahmad Noor Hishamuddin, group problem solver with a sharp mind, known for her bright energy, with ID B122410454. Next is Nurulain Sofea binti Noor Hisham, a beacon of creativity and kindness, with ID B122410474. And finally, me, Harith Iqmal bin Rahim, with ID B122410459. This is Hisham's family, a beautiful bond of togetherness. Hello everyone, in this presentation, I'll introduce the key objective of our project. First, we focus on developing technical skills in using specialized equipment for audio recording and image capturing. This allows us to reproduce high-quality sound and visual efficiently. Second, we apply advanced signal processing techniques, including convolution, Fourier analysis, the forced Fourier transform, and the various filtering methods to enhance audio and image. Next, this project encourages creativity by manipulating harmonics and sinusoidal signal to compose and synthesize music, showcasing both artistic and technical abilities. Lastly, we utilize MATLAB to analyze and process both audio and image data, demonstrating pro-efficiency in a powerful engineering tool. These skills are essential for modern audiovisual application, and I look forward to sharing more detail as we progress.
Task 1. This task is about understanding convolution in signal processing. We started by recording our voices, each saying our name, and used MATLAB to combine them with an impulse response through convolution. The result is a single sound that blends all three voices with the impulse response. We'll play this sound during the demo later and show it waveform to explain how convolution transforms signals. This helps us learn the basics of convolution and its effects on audio processing. This MATLAB code demonstrates the process of audio signal convolution, which combines two signals to produce a modified output. It can be divided into 5 steps. First one, the audio file is loaded using the audio read, and then the signal is normalized to prevent clipping. And then second, we generate a 440 Hz sine wave lasting 0.5 seconds as the impulse response. This actually represents a filter that will shape the original audio signal during the convolution. The impulse response is normalized to maintain the consistent amplitude. And then third one, the convolution is performed using the command of convsim, which combines the audio signal with the impulse response. This steps actually to modify the original signal based on the characteristics of the impulse response, and then creating a transformed version. The convolve signal is then normalized to prevent amplitude issues. And then fourth, 3 signals, the original audio, the impulse response, and the convolve signal are plotted. The plots show how the signals interact over time, with the time on the x-axis and amplitude on the y-axis. And then lastly, to better understand the results, this script plays the original signal, the impulse response, and the convolve output in sequence, showcasing the transformation caused by the convolution. Hence, this code illustrates how convolution combines two signals to produce a new output, oftenly used in audio filtering and also signal processing. The figure shows how convolution works in signal processing with 3 plots, the original signal, the impulse response, and the convolve signal. The first plot, which is the original audio signal, is actually the raw input sound varying over time. And then the second plot shows the impulse response, which represents how a system or environment reacts to sound like adding reverb. And then the third plot, which is the convolve signal, is where the impulse response is applied to the original signal, modifying it to reflect the system's effects. In short, the convolution combines the original sound with the system characteristic. It is widely used in especially audio effects and processing.
Hello, my name is Nurulain Sofea binti Hisham, and my matrix number is B1224104744.
Hi, my name is Harith Iqmal bin Rahim. My matrix number is B12241045.
Hello, my name is Insyirah binti Ahmad Hishamuddin, and my matrix number is B1224104554. And this is our task 1.
I'm excited to walk you through this code that generates a melody and visualize harmonic component inspired by Sofea. First, we set the amplitude to 10 for sound intensity with a sampling rate of 42k points per second. Each note lasts 0.2 seconds and we limit the melody to the first 10 seconds. We define the melody using example frequencies. The code calculates how many notes fit within 10 seconds and trims any extra. Next, harmonic weights are used to create richer sound. The loop generates each note by combining a fundamental frequency and two harmonic with lighter amplitudes. This creates a more complex sound by layering the wave. As notes play, we visualize the harmonic component in separate plot for analysis. Finally, the complete song is plotted and played using the sound function. This plot represents the harmonic component and the combined waveform of Sofea melody generated by the code. The top three subplots show the harmonic structure of a single note. The first plot is the fundamental frequency, representing the main tone. The second plot shows the second harmonic, which is double the frequency, adding depth to the sound. The third plot displays the third harmonic, triple the frequency, giving the note a richer feeling. The bottom plot is the full waveform of the first 10 seconds of the melody. Finally, the sound function plays the synthesized audio.
In task 3, I will explore how we can convert an image from the spectral domain to the frequency domain and back using the Fourier transform. I will walk through each step of the MATLAB code to explain how it does and how it relates to the signal and system theory. First, I will clearing the workspace. To start, clear the workspace with the clear all command. Next, I specify the path to the image file we want to process. I check if the image file exists at the given path using this function. After that, I display the original image using the image function. The title function is used to label figure as Hasya, Sofea, Iqmal, which represent the three of us. Next, I convert it into grayscale using the RGB to gray, and then the grayscale version of the image displayed in new figure window. After that, the variable S contains the magnitude of the Fourier transform. I display the shifted Fourier spectrum in the new figure. Next, I display the log transform Fourier spectrum in the another figure. Finally, I display the reconstruct image in a new figure. This process highlights the fundamental concept of Fourier transform in signal and system theory. It shows how we can decompose an image into the frequency component and then reconstruct it, preserving the essential information. This is the output that I got. First is the original image. The label is Hasya, Sofea, Iqmal, which is represent the three of us. Second, we got the grayscale image. Third is Fourier transform, magnitude centrum. Next is center Fourier transform, and then log transform spectrum, and final is reconstruct image. Last is task 4. Task 4 is about image processing using two techniques. First is Gaussian blurring. Gaussian blurring is a technique to smooth an image by reducing noise and details.
Each use a Gaussian kernel, a bell-shaped curve to blend pixels value with their neighbors. Second is edge detection using the Laplacian of Gaussian, a method to detect edge boundary of object in an image. The Laplacian operator finds region of rapid intensity change, while the Gaussian smooths the image to reduce noise before edge detection. This is the coding of the task 4. First is image loading and processing. If the image is in RGB format, it is converted to the grayscale. Next is displaying the original image to applying Gaussian blur. After that, I do the edge detection with the Laplacian of Gaussian, LOG. It's same as before. I will display the original image first to applying the LOG filter. The image is convolved with the log kernel to produce an edge detected image. This is the output of task 4. The output shows how the standard deviation affect both smoothing, Gaussian blurring, and edge detection (LOG). Gaussian blurring demonstrates how increasing softens the image by averaging pixels of intensities over a large neighborhood. Edge detection (LOG) highlight edge by finding regions with the rapid intensity change where control the scale of detecting feature.
In this project, we use MATLAB to explore how signal and image processing concepts like convolution and Fourier analysis work in real-life situations. To go through one by one, in task 1, we learn how convolving voices with an impulse response change and show signals. And then in task 2, combining harmonics to create a song help us understand how different frequencies make complex sounds. And then in task 3, by using a fast Fourier transform, FFT, on an image showing how images are represented in the frequency domain and can be rebuilt. And then in task 4, we apply image filtering like Gaussian and Laplacian of Gaussian kernels to blur images and find edges, giving us a deeper understanding of image processing. Hence, we improve our MATLAB skills and saw how these concepts are used in practice. That's all from us, Hisham family. Thank you for watching.